Okay. Find the mass of the wire. Okay. So I'm going to give you a path. I'll give you a density function, and you have to find the mass of the wire. 5 through 10. Given a vector field, determine whether it's conservative, find potential function. I'm going to just tell you right now. If I ask you to find the potential function, you know it's a conservative field. So find potential. Find a path, parameterization. I'm going to give you two endpoints and ask for a parameterization along a linear path between the 2 points. Okay. Find the integral for work.
What's the thing say with the T?
Say that again?
It's parameterization.
Yeah, parameterization. Find integral for work along that path. That's along the linear path. I'm trying to write too fast here. Linear path. And then do a parabolic path as well. You know, we did one where you had to go from 0, 0 to 1, 1, and we did 3 paths. Parabolic path, linear path, and square root path, right? Similar to that is what you have to do. Okay. And then I asked for the work along one of those paths or each of those paths. But you know right up front, it was a conservative field. So you have two choices here. Find the work along one of those paths, or find the work given that it's conservative, find its potential function, find difference in potential. Okay? The easy way is, right, Teddy? Do it the easy way as opposed to the harder way.
I don't think any of this is easy.
I don't even know what the two ways are.
Okay. One way is you find the work along a path. I can do a problem like this for you if you want.
Oh, wait, was this the stuff with the T's and we did it the other day, and there was that double integral and...
No. The double integral is for Green's theorem. This is for finding the work done in a path in 2 space where you just find, you're going from here to here.
Yep.
It's a conservative vector field. Set up a linear path, find the work. Okay? Set up a parabolic path, find the work. But you know it's a conservative vector field, so if you find the potential, you can find the work by taking the difference in potential.
Mm-hmm.
So those are the two ways. Find the work along a path or find the difference in potential.
Okay. I'll pretend I get it.
Thanks, Teddy. 11 through 13. Oh, this is a vector field in 3 space.
Oh, man.
I'd expect you to be able to find the curl.
I had some trouble with that.
Oh, really?
I don't know if it was just like the WebAssign, question getting in my head.
Oh, really? Wow. Find the curl and then find potential function.
I was close. It was just like...
I mean, I'm pretty good at working out my traps, but like curling, I was never really good at doing that.
Oh, see, that could hurt you, yeah. Yeah, you really need some good ice and some good sweepers, too.
Yeah.
Yeah.
That's true.
Could be a tough test. Yeah.
You said this was easy.
Well, if your sweepers aren't good, it could be a tough test. All right, last one. I give you a vector field, okay, and a rectangle, and you got to find the work 2 different ways. Find the work along each edge. Okay, and verify the sum of the works along each edge. Find the total work that way, and use Green's theorem to find the total work. and the two should agree. Okay? That's your test. I think that's more or less what I said the other day. And that's what it is. I can do any problems you want me to do? Yes.
Can you do the 11 through 13 one?
11 through 13, find the curl and potential. Let's do it.
Yeah, that'd be helpful.
Okay.
Wait, when's the homework for this chapter due?
18.
18th, Friday.
Oh, this Friday? Okay. I got some work for me.
Okay, let's do find the curl. All right, so I got to give you that then. Okay, so let's say given field is equal to y squared z cubed, 2xyz cubed, 3xy squared z squared. Let's say you're given that field,
Was it the second?
2xyz cubed. That'll do it. That'll do it. Whoa! That'll do it. Let's go back it up a little bit. All right, first thing is to find its curl and then determine whether it's conservative. And if it's conservative, find the potential function. Okay? So let's do it. Find the curl. I, J, K. Partial with respect to x. Partial with respect to y. Partial with respect to z. M, N, P. Definition of curl. I, J, K. Partial with respect to x, partial with respect to y, partial with respect to z. Y squared z cubed, 2xyz cubed, 3xy squared z squared. Holy mackerel. This is going to be impossible.
Probably.
All right, let's do it. Let's see what happens.
It goes, which order does it go in? The MNP?
MNP, yep, MNP. Okay. Cross this out, cross that out. Partial of 3x y squared z squared with respect to y. 6x y z squared. Attaway, Jamish. And then, okay, so let me write it out. So it's 6x y z squared minus partial of 2x y z cubed with respect to z. 6xyz squared. Wow, that's pretty interesting. Okay. I know it. Let's do the next one. The next one is you cross this out and you cross the middle column out. We're going to have to take the partial of 3xy squared z squared with respect to x. Nice. Minus. Next we have to do this one with respect to z. What's the partial of this with respect to z? Whoa, that's interesting. Last. Okay, cross this out, cross this out. Take the partial of this with respect to x. 2xyz cubed minus partial of this with respect to y. Partial of this one with respect to y. What the heck? Holy mackerel, what do you get? 0, 0, 0. The curl is identically 0. It's the 0 vector. That vector field is said to be irrotational. The field is conservative.
Why is it conservative?
Because the curl is 0. As long as this curl comes out 0, it's conservative. Yes?
Isn't that at all?
The unit J for that function, 3y's.
Yeah, you got to take the opposite of it.
Okay, okay.
Good call, good call. You know, I was thinking about it, and then I said to myself, it's 0 anyway. I knew it was 0, and then I didn't bother with it. But you're absolutely right. There should be a negative in there. Okay, so it is conservative. So now we can find a potential function, or its potential.
Wait, if it's negative, wouldn't that be something negative?
No, it's still 0. You get 0 here, take the opposite, you're still going to get 0. No getting around it. Okay, so the function we have, we're looking for its potential now. And what you would do, this is the gradient, therefore, to some function of 3 variables. This is the gradient to some 4th dimensional vector space. The partial of this vector space with respect to x is going to be y squared z cubed. That's how you find its gradient. The gradient of this potential is this. So this is its partial with respect to x. The function, therefore, to find the function, to find that potential, you integrate with respect to x. What's the integral of this with respect to x? X y squared z cubed plus possibly a constant that is in terms of y's and z's. Because in that context, the integral with respect to x, y's, and z's are constants. What else do we have? Well, if our vector field is going to be the gradient to some function of 3 variables, then the partial with respect to y must be 2x, y, z cubed. So our potential must be the integral of this 2x, y, z cubed with respect to y. What's the integral of this with respect to y? Oh, z cubed. I forgot the z cubed. Plus possibly a constant that's in terms of x's and z's. Well, in addition to that, the partial of this with respect to z would have to equal this. Therefore, the integral of this with respect to z, which is going to be x y squared z cubed over 3 is x y squared z cubed, plus some constant in terms of x's and y's. We have to reconcile the 3. We have to come up with one function that meets all 3 requirements, and that one function is?
It's impossible to say, really.
X y squared z cubed, and that's the potential function.
Probably just circle.
And that's what you got to do for that question. So what I had to do when I just made this thing up, I had to do all this and adjust it so it came out 0, and then that's what I had to do.
Wow.
I had to do all this in my head.
That's
I know.
impressive.
Or I could have started with this and took what's partial with respect to x, partial with respect to y, partial with respect to z, and done it that way. All right, but anyhow.
Or you could have just stolen an example right off the test.
It's true.
So you
I
know
don't
I
do that.
You know what? I wouldn't be surprised. I'm not going to look at the test now. I put the test away. I would not be surprised if that's it, too. All right, Dylan.
Do you know who invented that curl thing?
I do not.
Was it you?
No, it's not me.
Top here.
Yes. You have a question.
Yeah.
Bring it up.
Just joking.
That's pretty funny. That's pretty funny. Wait, I'm supposed to read this? Is that what you're telling me?
They weren't really.
Oh. Okay, here we go. Let's do the line integral f dot dr. Okay. F is y e to the xy, x e to the xy. The first path is t, opposite of t minus 7, and t goes from 0 to 7. And then there's another part that runs off the side here. Let's do this first.
Okay.
Okay? There you go. Okay, let's do it. How do we do that? Line integral, we change it. So it's in terms of the parameter. They give us the parameter. This is going to be x. This is going to be y. So we can rewrite the field in terms of the parameter. The field then is y e to the x y. Oh boy, this is not looking nice. Okay. X e to the xy. Okay. That's a parameterization of the field in terms of the parameter there, in terms of t. Dot r prime 1, negative 1, dt. And t is going from 0 to 7. Okay. That's how you would do that. Okay. You ready? I don't know. I'm not sure. Let's see what happens here. There's other instructions. It said or.
If it's an easy way or something.
There's an easier way of doing it if
Yeah.
I think what they want you to do is just find the potential and then
take the difference in potential.
Because
All
it'll
right.
end up being 0.
Is that right?
Yeah.
That's funny. Well, let's see what happens. And if I run into a big roadblock here, a big mess, then we'll look at the potential, because the potential is not very difficult. It's clearly, oh yeah, it's not that bad. All right, let's see what happens though. So you get 1 times this minus this. This is bad. dt. Yeah, this is bleakness. I was hoping that something would cancel out here, but it doesn't even cancel out. You just get a negative 2.
You can just take the power coming out.
Yeah, you can take that out, but that still doesn't really help, because you end up with this minus t, which is minus 2t plus 7 dt. The first integral is not bad, because that's just an e to the, no, even that's, wait a second.
How do you get 9
I don't know if
Oh, wait, we can do it. This is easy now. I see it now. Go ahead.
No, go ahead.
Okay.
Oh, yeah, you
Yeah.
With e to the negative t and parentheses t minus 7, could you make that t squared plus 7t and then do this u substitution?
Yeah, that's exactly the way to do it. It's a negative t squared plus 7t. And guess what? The du part is negative 2t plus 7. That's exactly right.
Oh.
It's an e to the u form. U is equal to, the du is, look at it, you get negative t squared, which is negative 2t plus 7. Ha!
Just know they planned it that way.
Yeah, they did. They had to. Okay, so it's e to the u du form, and the integral is e to the u from 0 to 7. I mean, it's perfect. Put in the 7, you get e to the 0, which is 1, minus, put in the 0, you get e to the 0, which is 1. You get just what Liam said. You get 0. That's pretty funny. That's pretty cool.
That's
Let's-
like always.
Let's say that
First thing you gotta try is just 0.
Yeah.
I'm just gonna circle it. I want to see what happens.
Probably a good
Can you leave that
chance.
up there for another second?
Yeah,
Thank you.
probably got a good shot at there. But let's do the potential there, and let's see what we got. Yeah.
What would that be on the exam specifically?
This would be
How is that?
the work,
Line integral.
the line integral. Yeah, this is a line integral.
Conservative function.
Yeah, parabolic. Yeah, that would be the line integral one.
So 5 through 10?
That would be like 5 through 10, yeah. Yeah.
So what are we missing? So what we have done the parameterization of it. We found the integral of it. This is for work.
Yep.
And what's parabolic path then?
Well, this one here is not a parabolic path. This one here is a linear path. A parabolic path, if you're going from 0, 0 to 1, 1, say, you've got to get it along y equals x squared.
Okay.
But I'm going to try to get the
Potential.
potential out of this. Let's see if we can do that. Okay, is everybody okay with this?
After you do that, could you
Hold on.
What's that?
after that, could you re-explain the parameterization thing and maybe a simpler problem?
Sure. Yeah.
All right.
Okay. let's take a look at this. Here's our field. And what we want to do is see if it's conservative. Here's M, here's N. Take the partial of N with respect to X. And when you take the partial of this with these, oh, you got a product rule, huh? It's first times the derivative of the second, which is e to the xy times y. The derivative of e to the u du, plus second times the derivative of the first, which is just plain 1. So you end up with this as the partial of n with respect to x, partial of m with respect to y, product rule, first derivative of the second, plus second times the derivative of the first. Well, that's amazing. That's pretty cool. So it is conservative. The two are equal to each other. What we're going to do is capture this potential by integrating this one with respect to x. Now, when you integrate this with respect to x, it's an e to the u form. U is xy. The du is y dx, and it's there. Okay? So you just integrate that. You get e to the xy plus a constant, possibly in terms of y.
So you integrated in the x is so the y just disappears?
The y's are constants. The x is the
So you
variable.
bring out the y, right? Am I correct?
This y serves as the du because I'm integrating e to the
That's
u
right, you
form.
put it- So the u is the xy.
Yes, it is. Exactly right. Also, my potential is the integral of this one, x e to the xy, with respect to y. U is xy, the du is x dy. Well, I have it. Okay? This is e to the xy. Therefore, my potential function is e to the xy. The difference in potential will give us the work. Okay, so the work is my potential at the end. Well, let's see, what is my potential at the end? My t is going from 0 to 7. So here's the start point is 0, 0. The end point when t is 7 is 7, 0. Is that right? No, that can't be right. All right, I messed up. When t is 0, I get 0, 7. Shoot. Okay, at t equals 0, I'm sorry. I get 0, 7. That's my starting point. At t equals 7, I'm at the point 7, 0.
How are you getting those points?
I'm going back to my definition of my parameter, which is t, opposite of t minus 7. That's what they gave us. So I'm letting t equal 0 to find out where I'm starting, and let t equal 7 to see where I'm ending. So I'm putting a 0 in here and getting 0, 7. I'm putting a 7 in here and getting 7, 0.
Because we're moving from 0 to 7.
Yes, yes, they tell us that. They gave us that. So my potential at 0, 7, okay, would you put that in here? So what I'm going to do is find the work by doing this. Okay, 0, 7 is, put a 0 and a 7, you get e to the 0, which is 1, minus 7, 0. You still get e to the 0, which is 1, and you still get the same 0 joules of work. Yeah?
You get your potential.
What's that?
You get your potential, then you take your endpoint, you plug it into your position function, you take the values of x and y you get from your position function, and then plug it back into your potential.
Okay. Generally, you're given the x and y points of your start and end, and you have to find the t values. But in this one here, they gave you the t values and the parameterization. They didn't give you the x and y, which is unusual. but that's what happened here.
So is it always going to equal the same answer for the potential and what we did before?
Absolutely. As long as it's a conservative function and has a potential
So
function.
just two different techniques.
That is correct.
So the first technique, what's that called?
That's finding the work along the path.
Okay, and this is just finding the work using
Potential. Yeah.
So is it always, if it's a conservative, f of x to the y is always going to equal to each other, correct? Because you got e to the x and y.
Well, no, these don't necessarily have to equal each other at this point. We had one the other day where they're different, but you reconcile, you come up with one function that satisfies both requirements.
Okay, is there something going to be like that on the test, or?
Yeah, that would be the work done along the path.
No, I'm saying one that won't have them equal to each other.
I don't know, but there'll be, if it's conservative, you can find it.
Like, would you be able to do one like that specifically? There?
Let's see. I can come up with one. You ready? I think. I did one before. Let's do one. Let's do it. We can do it. Let's suppose this is our field. This is going to be, so if I do x1, will this work? Partial of n with respect to x is 0. Partial of m with respect to y is 0. So it is conservative. Okay? So watch this. We can do this.
We were just figuring out, anyway, we might just.
Okay.
What are we doing here?
I'm giving you a field
Yeah.
that is conservative. We're going to find its potential function, but it won't be the case that it comes out to be the same thing like this one did, e to the xy. Or the previous one did too. What's that? And then we're going to have to reconcile. But it's pretty clear-cut what you have to do.
So in order to use potential, they have to be conservative. If they're not,
Absolutely
if
right.
they're not conservative, then it's a D, like, we don't use it.
You can't use it. Matter of fact, if it's not conservative, it won't have a potential. You won't be able to find one. It's impossible.
Okay.
But let's do this one.
So that probably won't happen on the test then.
That's right. I won't ask you to do the impossible. Although there's a motto for something that
The physics.
the unlikely we do today, the impossible we do tomorrow, or something like that. Somebody has it. All right, but anyhow.
Yeah,
maybe.
there's exams.
All right, here's what you got to do. It is conservative. Let's find its potential. Let's take the integral of the first one, x, with respect to x. You get x squared over 2 plus possibly a constant in terms of y.
So you're finding it,
I'm finding the potential,
okay, so integral of x.
the integral of x, and now it's also equal to the integral with respect to y. What's the integral of 1 with respect to y? Y. Now here's one where these are not the same, but you can still reconcile the two by coming up with a function that meets both requirements, namely x squared over 2 plus y. That would be your potential function, because it has this requirement and it has this requirement.
So you just add them together?
Yeah, well, yeah, that would work in that case. As long as you come up with one function that meets both requirements. And how do you know it's true? Take the partial with respect to x, you get x. Take the partial with respect to y, you get 1. That's
How you
it.
check.
That's how you would check.
So what if you did so you could do a partial integral?
That's what you're doing, 2 partial integrals.
And then you just add them together. Is that always the case? You just add them all together?
Well, you got to reconcile the two. Sometimes, I mean, in more complicated cases, some parts will be equal and some won't. The equal part you keep, and the other part you have to bring them in.
So do you just plug it into the constant x, c to the y and c to the x?
Yeah.
That's all you're doing? So you're plugging into c to the y, you're plugging the bottom.
The y one, yes, and the c constant in terms of x is the x one.
And that's okay to just add them together like that?
Yeah. What's that?
As long as it's a constant in terms of y.
Yeah, as long as you meet these requirements, you can do whatever. What's that?
So long as if like the second one there was x, y,
You wouldn't be able to do that.
you wouldn't be able to do
Yeah,
that.
correct.
Because it has both an x and a y.
So what would you do then?
then it couldn't be done. Then you don't have a conservative vector field. Then you have no
So-
potential.
So if it's conservative, then pretty much you'll be able to add them together because, you know,
Or else it's equal to it. So it really, that part of it usually, almost always, is not difficult. Though it's obvious. You look at it, you say, okay, I got to come up with one function that meets both requirements, and it's pretty clear cut. Liam,
Can you just set up how a massive wire will be set up? Just like set the problem up, like what's going to be given?
here you go. You ready? Mass of a wire. A mass of a wire, you're going to be given, now we're limited in the number of, do I actually have you do it out? If I have you do it out, I have to give you a real
oh
simple
man, he's
one.
gonna look at the task.
I'm going to look at it. Oh yeah, I asked you to do it out. So, it's, hey, but what that, what that means is,
Too late to withdraw.
what that means is, I'll give you one that's going to be linear. It's going to be real nice and simple.
Sophie's exams are like that.
All right, let's say this is 1/8 here. Here's the wire. All right. Now, I'm going to give you a density function.
I'm glad Toby.
Let's say the density function is x. All right, I want you to be able to set up the line integral that gives me the mass of the wire, set up the parameterization along this line, and then find the mass of the wire. Okay? First thing to do is set up the parameterization.
There's going to be multiple questions like this.
Yeah, there are, it's 1 through 4, so there are 4 questions.
Then after this, could you do another one where you set the parameters? Or find
Yeah, that's what we're going to do right now. We're going to find the parameterization.
T18?
What's that?
Could be T18?
Yes, that would be the easiest one. What you want to do in that case is come up with the equation of the line. The equation of the line is y equals 8x. Okay. Once you have the equation, y equals 8x, the parameterization usually is pretty straightforward. Let x equal t, and then find out what y is. Okay? If x is equal to t, y is going to be 8t, and the t will go from 0 to 1.
So is that given to us? Or no?
No, that may not be. The endpoints would be, and I'd ask you to come up with a parameterization.
So y is equal to 8x.
Yep.
Where does that t come from?
Well, we got to set up a parameterization, and the way to do that is to let x equal t. You do that, and then find out what y is. Y is 8 times x, or y is 8 times t.
It'll be t over 8.
No, it's 8t, just what I have right here. This is the parameterization, t, 8t. It's possible that I'm going to say, set up a parameter. I'm going to tell you what I say. I'll give it to you. Oh,
You just give us her.
I give you both of them. There's 2 different parameterizations. I just gave you both of them.
So in other words, you give us a
Yeah, I'm going to give you the t, 8t. Anyways. Or it could have been e to the t, 8 e to the t. That would work. It could be cosine t, 8 cosine t. That would work. As long as the y is 8 times the x, it doesn't matter if you use a trig function, exponential function, whatever, that will be a linear path. Now what will change is the speed at which it goes along the path. But for the mass, it doesn't care. Okay? It doesn't care. The mass of a wire is independent of the parameterization as long as you start at the same place, end at the same place, and stay on the line. If you do that, it doesn't matter if you use sines, cosines, e to the t's, inverse trig functions, whatever. As long as you have that y component 8 times the x
So we
component.
just need to know how to do the t's and stuff for that last one then. Right?
Well, I'm going to give you the parameterization anyways.
Yeah, but for
Yeah.
the
Oh, let's do it. Yeah, for the mass?
no, for the
Oh.
The one with the lines and
Oh, the one around the rectangle.
yes.
Yeah, that one you're going to have to set up the parameterization. That one you
Those are the
will.
words I was looking for.
That's like
Yeah.
half the problem.
What's that?
So that's like half the problem.
Yeah, it is. Yeah,
That's the
it's
whole
true.
problem.
Yeah, well, yeah, it is a good portion of it, that's for sure. All right, let's do this. The mass is equal to. Okay. It's the integral of our density function, okay, ds. Okay, it's a line integral. What do? We evaluate line integrals by changing it to an integral in terms of t. T is going from 0 to 1. X, our density function, in terms of t, you go back to the parameterization. This is x, this is y. It's t.
So your density function was xy, you'd have 8t squared.
You bet you would.
Okay.
Okay? If the it's a good point. If the density function were xy, you would have 8t squared right in here. Okay? Because this gives you your x and the y. Then you have the square root of dx dt. Now, for the mass, it's a little bit slightly different thing there. It's dx dt, 1 squared, eight squared. Okay? So,
Root 65.
yeah, it's going to end up to be that. See, it's not the same as that dot r prime. It's you got to multiply by the magnitude is what we're doing here. So it's a little bit different. That's what we were doing with that problem somebody gave me the other day. And I wasn't sure if it was a mass problem or a work problem. There's slightly different approach to each one of those. So I started doing it one way, and I said, no, it's this, and then I went back to the original way because I realized it was really the mass
Set
problem.
up the magnitude of R.
Yeah.
The work is going to be R prime.
Yes, correct. That's correct. So this is it. Okay.
That's all. You don't even need to finish it.
So the mass is just the prime.
Yeah, the mass, no.
Or it's the
The mass is the magnitude. Yeah. So it's slightly different.
All right.
Okay, what else you guys want to do?
Can you do
Wait, all right. Go ahead, Danny.
All right. No, I got nothing.
Oh, okay.
Actually, before we move on, so
Can you do
Go ahead.
the parameterization is you just find the equation of the line and plug in your bounds, or plug in t for x.
Correct.
And solve for each one.
And solve for y.
And solve
unless
for
you're
y.
given
Yes, in terms of t.
Unless you're given t, right?
I'm going to give you both parameterizations. On this particular problem, there's two parameterizations of the same path, and I give you them
And
both.
that's for like all.
What's
of
that?
That works with the 3D case too,
The 3D case,
for finding the parameterization.
find the point. Oh, the second one is given, and I give you the points. And I ask for a linear path parameterization, and then I ask for a parabolic path parameterization that you're going to have to come up with. But here's the thing. When I ask for the parabolic path parameterization, I'm going to give you the equation y equals 2x squared. I give you that parabola. Let x equal t, y would be 2t squared. Okay? That's what you do. Okay, just so you know. Yes?
Do you want to do the rectangle one?
Okay, well, I'll set it up for you. We'll do as much as we can. Okay? The rectangle one is one where I'm going to give you a vector field. Let's make it non-conservative.
That was the whole test.
What's that?
Yeah, pretty much. I did the whole test.
Yeah, I think so. Yeah, I think we've done it all.
To take you tomorrow, or?
Yeah. Let's go around a rectangle. Let's go 0, 0.
Are you just going to give us endpoints?
Yes.
Okay.
So the whole exam's endpoint.
What's that?
No, just this problem.
Just problem.
No, for that one, he gives endpoint too.
Yeah, but I'll give you the parameterization. This one, you're going to have to come up with it. Okay. So here we go. We're going around this rectangle. We're in this vector field. We want to find the work done. Okay. So we need to find the paths. Let's find the first path. First work, we need R1 of t. Now, R1 of t, and I want t going from 0 to 1. Okay? So, what is it? T comma 0 is perfect. Okay? So, the first piece of work is 0 to 1. Okay. X x, this is x, t dot r prime 1, 0. I'm not going to do this out. This is easy enough to do. You guys can do that. Okay. Second piece of work.
Now that's dot R prime for its work.
Yes, yes, yes. Second, we're going this way. 1. Now, I want t going from 1 to 2. And this is how I'm going to do it on the test. I'm going to say that find the parameterization,
So be 14.
and you got it?
Is it 14 or
Well, yeah. Well, you don't actually have to write out the parameterization, but you do have to find the work. So actually, it's up to you to set up a parameterization any way you want it. But I'm going to set it up from 1 to 2.
Where did the
Okay?
TT come from?
Say that again now?
Where did the TT come from again?
This came from my field is XX, but X is equal to T. Okay. I want T going from 1 to 2. Okay. Now, and here's, that's good. That's exactly right. Here's how you do this. This is increasing by 4 units, the y coordinate by 4 units. The t is only increasing by 1 unit. That tells you the coefficient of t has to be 4. Okay? It has to be 4. Now, if t is equal to 1, this would start you at 4. You don't want to be starting at 4. You want it to start at 0. Subtract 4 to make sure it starts at the right place.
so if you plug in 1, that's pretty much
Yeah, that'll do it. You can verify it by plugging in the endpoint, but it always works. Okay? If you plug in the 2, you get 8 minus 4, which is 4, and that's where you want to be.
We're plugging into where?
Why is the X 1?
The x is 1 because it stays at 1, the x coordinate.
Oh, okay.
Plugging into where?
You plug the t equals 2 in for t here to verify that you end at the right place.
And then up there, y is going to say 4. Yeah, all right.
Okay, so the second work, okay, 1 to 2, x, 1, 1, dot, 0, 4, dt. Okay? That would be the work and moving up the side of the square, the rectangle. Now, I'll let you guys do that. Third piece.
Why 0, 4?
0, 4 here because it's r prime. And r prime of t, there's 0 here and a 4 here.
Oh,
This you get from the
then why is
derivative.
top one 1, 0?
Because the derivative of this is 1 and the derivative of that is 0.
All right.
No problem. Third one, you're going this way. Negative t, no, and the t's are going from 2 to 3. Okay? 2 to 3. So it's negative t.
Are we given the 2 to 3 all the time, or do we just assume it? It's always given.
I would make that assumption, but you don't have to do 2 to 3. And the way I've got it set up, I ask for the work here, work here, work here, work here. You can set up any one you want.
So technically, we can use any numbers higher than 2.
You can use any numbers you want as long as you start at the right place, end at the right place, and stay on the path. Okay? I'm telling you, this is the way it's normally done in the real world. It's a sequential thing. 0 to 1, 1 to 2, 2 to 3, 3 to 4.
Okay, that makes sense.
Negative t plus 3.
Let's check it out. Negative t plus 3. If you're starting t at 2, this is negative 2. But I want to start at 1. Add 3. What's my y coordinate? Y component?
4.
4. Okay? They all set on that?
Wait, why would we? Oh, because it doesn't change.
Doesn't change. W3, the third piece of work, the integral from 2 to 3, x, negative t plus 3, negative t plus 3, dot r prime, okay, negative 1, 0, dt. Okay, you guys ready? No? Last one. W4. That is x coordinate, x component, 0. What about the y component?
Minus,
Negative 4t plus 4.
divided by 4, no?
No, negative 4t, that's your start because that's decreasing by 4 units. Now you got to make sure that you start and end at the right place. When you when you start at 3, you're going to have, no, it's not going to be plus 4. If you start at 3, you're going to be at negative 12. Oh my gosh. But you really want to start at 4.
Plus 16.
Plus 16 is what you're going to need to make sure you start at 4. Third piece of work, fourth, 3 to 4. Oh, XX, oh, this is interesting. XX, R prime. How much work are we doing coming down here? 0 work, because it's XX and every X is 0. So I have 0 work there because you have 0 force along that y-axis. Now, you add up all 4 pieces of work, you're going to get the total work and going around that rectangle. But you could also do the problem to find the total work by using,
Is it?
by what?
It's not conservative though, is it?
It's not conservative. So you could also do the work by doing Green's theorem.
Non-conservative.
So let's do it. Non-conservative, we're going to use Green's theorem. Let's do it. Double integral.
So if Green's theorem, you can only use it if it's not conservative.
Well, you can use it if it's conservative, but it's always going to be 0. Because Green's theorem is only used in a closed path. So, okay, so what do? You take the partial of n with respect to x, 1, minus the partial of m with respect to y, 0, dy dx. And y's are going to go from 0 to 4, and the x's are going to go from 0 to 1. And we get 0 to 1, we get a y.
How do you get 0 to 4?
Because the y's are going from here up to here. They're both constant.
Oh, that's right.
So 0 to 1, 4 dx, 4x, 4 joules of work. And if you were to compute each of these rectangles and add them all up, you would get 4 joules of work. Dylan.
What's
Oh, like that. Oh, okay.
So, are we, what are we studying for our final?
I'm going to give you all the outline for the final on Wednesday.
On Wednesday, right after the exam or before the exam?
Wednesday, Tuesday's the exam.
Oh, yeah.
Wednesday, I'm going to go over the exam and then say this is what's on your final. And I'll give you the topics, pretty much
It's Monday at 8.
everything.
Is there going to be a lab 6?
There is a lab 6. There is a lab 6. Wow. I don't have time to do it today, though. So there is a lab 6. Some people have already done it. It's the centroid of the triangle.
No, that was lab 5. Yeah, that was 5.
Oh, there is lab 6?
So there is no.
There is lab 6. Wait a second. You guys got a second? Here, I can show it to you.
Was the density thing.
Yeah, that's lab 5. Here's lab 6. Watch this. I'm going to just show you. This is it's pretty straightforward. Okay?
Stop recording.
Stop recording? Okay.